uh, we try to understand the concept of relative motion. In the previous class, the TA taught you about absolute motion, right? This is about relative motion, and we'll see how to use the relative motion formula to compute velocity and acceleration and so on. So, brief overview of what we need to know and what exactly is relative motion. Okay, we assume a ground frame or a fixed frame, or it's also called the reference frame. Okay? And we're interested in tracking the motion of a point B. So this is, let's say it's a particle whose motion we want to keep a track of. Okay. Now you could write the position of B with respect to the ground frame. That's what we do, right? So if you want to find the position of, say, an object in this room, let's say that table, you know the position of that table with respect to a frame, a coordinate frame, which could be one of the corners of the room. Okay? But there's another way of doing this, and that actually is good for certain scenarios, which I'm going to talk about in a bit. Instead of keeping a track of B from from the frame X, Y, Z, we keep a track of B from another frame. I'll call that X prime, Y prime, Z prime. Okay, let's call the origin A, and this frame is translating observer. Okay, so the frame A itself is moving, and assuming B is also moving, then what you do is you keep a track of B with respect to A, and you also keep a track of A with respect to the fixed frame, and that is how you can keep a track of B with respect to the fixed frame. In other words, what that means is, and I'll give you an example where this might be useful, is if you want to keep a track of B, okay, there is a position of A plus the position of B with respect to A. So in this vector equation, we have B is the position of B with respect to fixed frame. I'll call that O because that's O. RA is the position A with respect to fixed frame O, and RB with respect to A is position of B with respect to frame A. So it's often best to show this by vectors, and the direction of the vector is very important. So I'm going to draw a vector from O to A. That's my RA. I'm going to draw a vector from O to B. That's my vector RB. And then I'm going to draw a vector from A to B. This thing is RB with respect to A. So what you want to remember is when I say B with respect to A, the vector goes from A to B. The vector goes from A to B. The direction is that way. when I say RB, it really means B with respect to O, but you don't really put O because it's understood that that is the fixed frame. The vector always goes towards B. The vector goes towards A with respect to O. So always remember whatever is here, that's how the vector points. Okay? If you draw it the other way, it's going to be the negative of that vector. So that's how you relate it, right? This basically completes this closed loop, and the vector equation makes sense. So where this might be useful, well, think of if let's say that you are traveling in a bus, okay, and you're moving inside the bus, then you're going to be the object B, the bus is going to be A, and you want to track the position of yourself from the ground. Then what you can do is, one way to do it is you keep a track of the bus, how fast the bus is moving. You keep a track of how fast you are moving inside the bus, and that's how you can keep a track of how you are moving with respect to the ground. That's why you need this equation. It makes your life easy because you do not have to keep track of yourself when you're moving inside a moving frame, in this case the bus, with respect to the base frame. So it's just a matter of convenience. You could do it the other way too, but just that turns out it's much easier to display. Another application would be if you're flying in space, like there's a rocket and something is moving inside the rocket, then that object would be B. The rocket itself is A, and you want to keep a track of the rocket with respect to ground. You also want to keep a track of the person with respect to ground. Or it could be two satellites, right? A and B. You keep a track of a satellite with respect to a planet, and that you can keep a track with respect to the sun. Okay, so that's the equation for the position. The equation for velocity and acceleration is simply the derivative of this. So velocity is simply velocity of B is velocity of A plus velocity of B with respect to A. Again, the direction of vectors is the same. You need to go from O to B, O to A for the first two, and then A to B for the second term on the right side. For the acceleration, it's as simple as taking the derivative of the first expression, of the velocity expression. It's AB equals AA plus AB with respect to A. Is that clear? Okay, so first question. Two boats leave the pier P at the same time and travel in the direction shown. The velocities are constant as shown in the figure. So you can see the velocity of B is 30 feet per second and A is 40 feet per second. Find the velocity of A relative to B and the time when they are 1500 feet apart. Assume T is 0 when both are at P. Okay, let's do it one at a time. So the first part, we need to find the velocity of boat A relative to B. Right, that's the unknown. So this is a straightforward application of the formula. Velocity of A is velocity of B plus velocity of B with respect to A. Okay, now that doesn't quite have what we want, A with respect to B. Well, if you want to find A with respect to B, it's simply you got to flip the sign and the. So you could also write this as. So there are multiple ways of doing this. You can write VB equals VA plus V. I think I made a mistake here. This is not right. Huh. Sorry about this. This should be A with respect to B. My bad. Okay, so that's right. So we can easily, if you find VA and VB, we can find A with respect to B. If you are asked the other way around, if you are asked to find B with respect to A, we switch. We can actually find A with respect to B first, and just switch the signs on that, right? Because vector from A to B is the negative of the vector from B to A. Okay, so we only need to find A and B in order to find VA with respect to B. So let's find V of A. Okay, so A is traveling at 40 feet per second. Okay, it makes an angle of 30 degrees with the vertical. So what's velocity of A? So it's 40. Is it cosine 30 or sine 30 for A? Sine 30. Is it positive or negative? Should I put a negative sign? Or it's positive? So look at the arrow. The arrow is pointing this way. So when I resolve it, it's going to point that way, to the right. So it's positive. What about the y component is going to be simply the cosine of 30 degrees J. Again, the vector, this, when I resolve it along y, it's pointing upwards. When I resolve it this way, it points upwards. So that's going to be positive. Okay, VB, so that's 30 feet per second. And it's at 45 degrees. So that's going to be same reasoning. In this case, when you resolve it along the x-axis, it's going to be cosine of 45. And when I resolve it on the y-axis, it's going to be sine of 45. So 40 cosine of 45, sorry, 30 cosine of 45 plus 30 sine of 45 degrees. Okay, so VA with respect to B is VA minus VB Okay, I'm just going to write the answer, but you need to take the sine, cosine, multiply, and so on. What I get is minus 1.2i plus 13.43j. So if you're asked to find B with respect to A, that's going to be negative VA with respect to B. Right, so you could potentially do that if you didn't want to use the reverse formula, which is VP equals VA plus VB with respect to A. Is that clear? Okay, second question asks you for the time when the boats are 1500 feet apart. So what's happening is so one of the boards is, let's say, here in time t, and the other board would be somewhere here. Is it the other way? Yeah, sorry, this should be A. So some point of time, the distance between the two boats would be 1500 feet. You got to find the time when that's true. Okay, so if you had no idea of using the relative velocity formula, then what you need to do is, you're given the velocity, you can find the position, right? You're given the velocity of A, you can find the position as a function of time, right? How will you do that? When you integrate the equations, you integrate the velocity equation to get the position with respect to time, position with respect to time, and then find the distance between the two, which will be a function of time, right? The magnitude, and that will be 1500 and solve for time. That's the long way of doing this. The short way is using the relative velocity, what I'm going to show you. Okay? So the short way of doing this is knowing the fact that S, the distance between the two, is simply the magnitude of the velocity times the time. So in the first method, which I just described, you need to integrate two equations and then take the difference. Here, you use the relative velocity formula directly without having to integrate anything. So S is 1500. Velocity of A is minus 1.21 square plus 13.43 square times time. So if you solve for time, you should get, well, it's 1500 divided by 13.48, which comes out to be 11126 seconds. Okay, is that clear? Okay, but you should try it the other way. Find the position from the velocity, find the position, and then find the distance as a function of position and solve for time. Okay, next question. Okay, so at the instance shown, car A is traveling on the straight portion of the road at 25 meters per second. At the same instant, car B, okay, is traveling along the circular portion of the road with a speed of 15 meters per second. Find the relative velocity of car B relative to A. So we want to find velocity of B with respect to A. So velocity of B is velocity of A plus velocity of B with respect to A. Now if you think that's hard to remember, okay, this formula, then this might be easier to remember. Velocity of B with respect to A is simply VB minus VA. So I don't think your formula sheet has this formula, but this is really easy to remember, right? You can forget about this, remember it this way. V with respect to A is velocity of B minus velocity of A. Always the first index is first, second index is second. Okay, so all we need to do now is find the velocity of B and velocity of A, same as previous problem. So let's try to do that for this particular problem. So A, let's try to find the velocity of A first. So A is traveling at an angle, and I've actually shown you the origin, it's x and y, but in a problem you may not be given the origin and the axis. You might have to draw that yourself if it's not given, because otherwise you cannot find the velocity if you do not have an origin and an axis. So we can see that the direction of motion of A makes an angle of 30 degrees with the x-axis. So this is 30 degrees. So in order to find A, we need to resolve velocity of A along the x-axis and the y-axis. So if this is 30, this is going to be 30 degrees. So what's the velocity of A along I and J? 25 meters per second. So 25 times, is it going to be cosine of 30 or sine of 30? Is it going to be sine for the I? So what's the component along the x-axis? Cosine 30, right? So cosine 30. Okay, the direction is along the positive x-axis, as you can see, so it's positive. So the y component is going to be 25 sine 30 degrees along J. And what's the direction? Is positive or negative? It's negative because it's pointing in the negative y direction. So negative. Okay, that was easy. What about velocity of B? Let's draw a similar figure for B. Okay, B is here. It's actually on the circular path. Makes an angle of 15 degrees, like so. So that's B. This is 15 degrees. Okay, so we need to, this is by the way a tangent to the circle. Okay, so what do you think? What? This is x-axis. This is y. This should be negative y, my bad. Okay, so my question is, we need to define this angle and this angle. So that angle is going to be, so there's a property of a circle that this angle, the angle made by the tangent to the horizontal is equal to the angle made by this arc with the center. So this is going to be 15 degrees. Okay. So this is same as this angle. So it's essentially going to be the same formula as that, except that we need to replace 30 with 15, and we need to put the appropriate magnitude for B. So it's 15 meters per second. So 15 cosine 30 degrees I minus 15 sine 30 degrees J. So B with respect to A equals, okay. Oh yeah, 15 degrees and sine 15 degrees. So that's going to be minus 7.162I plus 8.618J. Okay. So what you see is all the problems, it's a matter of drawing the right diagram and resolving the vectors in I and J direction and solving it. That's the key. Once you do that, it's super easy to find the relative velocity. Any questions on this?
So we
Yeah.
assign the direction that the car is going.
Yeah, you're told, normally you'll be told the direction the cars are moving. In this case, I guess it was not clear. It's supposed to be this way, yeah. And then sometimes you're not given a coordinate frame, so you have to choose one. Most times you will be given a coordinate frame. Any other questions? Yeah?
So we didn't need to use the rotor at all?
No, so okay, so this is a question in the book where they ask two questions with the same figure, so it's probably the a subsequent question would have used the row, yeah. Any other questions?
Just to find the difference in velocities at the coordinate vector,
Mhm.
just square them.
No, we don't square. So VB goes in here.
I know, but
Yeah.
just to find the magnitude, we can just square it and add it together. Square it.
Yeah, if you want to find, you're asking if you want to find this?
Yeah.
Absolutely. So if you want to find this, then it will be minus 7.162 square plus. Yeah, sometimes you're asked to find the magnitude, so this is what you'll do. Okay. Any other questions? Okay, so cars A and B are moving on a circular track as shown. Okay, I think this is A has speed of 90 feet per second and it is increasing at its speed at the rate of 15 feet per second square, whereas B has a speed of 105 feet per second. It's decreasing its speed at a rate of 25 feet per second square. Determine the relative velocity of A with respect to B and relative acceleration of A with respect to B. So unlike the previous formulas, this is a problem where the acceleration is non-zero, right? It's not uniform velocity. And the fact that you're given the speed and rate of increase of speed means that this is a problem where you need to take the velocity and acceleration in the normal tangential coordinates, right? To recognize the wording, increasing its speed. That's when we looked at problems involving NT-coordinates. That was the wording, precise wording. So it's an NT-coordinates problem, even though it looks like it could be done with IJ. Okay, so again, we're asked to find velocity of A with respect to B, which is velocity of A minus velocity of B. Okay, velocity of A. Okay, I've already drawn a coordinate frame for you. Okay, so we see that A um, is almost at right angle, so it's along the y-axis, and the velocity is pointing is tangent to the circle, which means that the velocity is along the x-axis. In fact, it's along the negative x-axis, so the velocity is simply minus 90 I, right? That's x or I, it's a negative. Velocity of B, however, is at an angle. So I'm just going to redraw the figure here so that we can resolve it along the axis. So this is B. The only information we're given is that the the line from the center to B makes an angle of 60 degrees with the vertical. Okay, so we need to find this angle here. Now this is a tangent to the circle, which means that this angle is 90 degrees. Okay, so what should this angle be? 30 degrees. Well, another way to see how why it's 30 is this is 60 and this line is parallel to this line, so this should be 60 degrees, right? And we know that the sum of all angles here along this particular line should be 180, so this should be 30 degrees for that to be true. In other words, 30, 90, 60 is 180. Okay, so we know what angle velocity v makes with the y-axis. That's good enough for us to resolve it along x and y. Okay, so velocity of B is the magnitude of B velocity, so it's 105 times, if I want to resolve it along the I-axis, this one, it's going to be, is it sine 30 or cosine 30 to get this? Sine 30, right? Because that's the opposite angle. So sine 30, and the direction is negative, is along negative I, so VB is minus 105 sine 30 degrees I. So obviously the J component is going to be 105 cosine 30 degrees J, and the direction is, well, if you resolve it this way, it's pointing in the positive y direction, so it's positive. So given VA, VB, we can now find VA with respect to B. I'm going to just write the final answer. It comes out to be minus 37.5 I minus 90.93 J. Okay, and since this is in feet per second, I'll put that down. Okay, so the next part asks me find acceleration of A with respect to B, which is simply the acceleration of A minus the acceleration of B. It looks exactly like the velocity formula, which means I need to find the acceleration of A and B, that's all, and I can find A with respect to B. Okay, let's try to do this for A first and then B. So A is moving this fashion, right? Its speed is 90, and so since the problem tells us speed is increasing, right? I would use UT, UN coordinates. So I'm going to draw UT and UN. Right, just because the question is worded like NT coordinates. So now I can write acceleration of A, this is A, is it's AT UT plus AN UN. Okay, AT is remember it's V dot. V dot is given to us as 15 feet per second squared, so it's 15 UT. And then for J, it's going to be V square divided by rho. So V square is 90 square divided by rho. Rho is simply the radius of the circle, which is 300 feet. Okay. However, we want to write everything in terms of I and J. So the question is, what is UT and UN? Well, UT is negative I.
Is this a circle?
It's moving in a circle. Right?
Oh, okay.
Yeah. So UT is minus I, right? This is along the negative I, and then UN is negative J. So we've written down acceleration in terms of I and J. Let's try to write acceleration of B now. So again, if you see the question, it gives you the speed and the rate of increase of speed. So we need to write in UT UN But the UT and UN I'm going to draw is going to be different from the UT UN I drew for this one, because remember UT UN changes with time. So B is at a different point on the circle. It's this way. So UT is going to be this way, and UN is going to be at right angles, but pointing towards the center of the circle. Okay, so we've seen that this is 30 degrees. So AB is again AT-UT plus AN-UN, which is its speed is 105 and 25 feet per second squared. So that's 25 UT, and V is 105 square divided by the radius of the circle, which is 300 again. It's decelerating, that's right. So I need to put a negative. What's that? 250.
Yeah.
Oh, it's a different radius? Oh. Yeah, this is. Okay, so my bad. This should be, yeah, this should be 250. Absolutely. So it's still in a circle, except that it's going on the inner edge of the circle. That's right. I did a mistake here. I've not put 250. My answers are not right. So it's 300. Okay, so the last thing which is left is I need to find UT-UN in terms of I and J, and then I'm done. Okay, and note that this UT-UN is different from that UT-UN. UT-UN changes as the particle moves or the car moves. So all I need to do is find UT in terms of I and J, find UN in terms of I and J, plug that in here, and then I can find A minus AB. So let me just do that. UT equals okay, so in order to do that, I need to resolve x along UT and y along UT. Okay, so to resolve x, it's simply I times cosine of 60 is pointing in the negative direction as UT. So it's going to be negative cosine 60 degrees I. For J, when I resolve it, it's cosine of 30 degrees, but that points in the positive UT direction. So it's going to be positive sine 30 degrees J. Then I need to get UN. I need to resolve I along UN and X along UN. Now to do that, what I'm going to do is extend this line. This angle is 60 degrees. This angle is 30 degrees. So in order to resolve X, it's going to be cosine of 30, but it's pointing in the negative direction as UN. So negative cosine 30 degrees I. And then if I take Y and resolve it along UN, it's going to be cosine of 60 degrees, but that's in the direction negative of UN. So negative cosine 60 degrees J. Okay, so I do not have the right answer with me because I made a calculation mistake. I didn't take this as 300. I'll write the answer later on, but this needs to go in here, and this fellow has to go in here. Then I need to take this AB, shove it in here, and this thing has to go right in A, and that will give me AB with respect to A. Okay, so I'll compute this, put it down, and post it. That's how you solve it. Okay, so I'm hoping that I'll get your grades out, exam grades by tonight, or worst case tomorrow night. Okay, and then we'll start with chapter 16 next class on Wednesday. I've already posted the pre-lecture notes for chapter 16. You can download and print them if you want.